Welcome back to Simplifying Synthesis. In this video, we're going to look at the total synthesis of Scabrolide A. This work was published by Zhanchao Meng and Alois in JACS in 2022 in their paper Total Synthesis of Scabrolide A and Nominal Scabrolide B. These compounds were first reported in 2002 by Xu et al. And were isolated from the Taiwanese soft coral Sinularia scabra. Scabrolide A was found to inhibit the production of interleukin 6 and interleukin 12 in vitro and has potential as an anti-inflammatory agent. Scabrolide A was first synthesized by the Stolz group in 2020, though the reported structure of Scabrolide B has never been synthesized, though it has been proposed as an intermediate in the biosynthesis of Scabrolide A. So let's start with the retrosynthesis. The researchers hypothesized that Scabrolide A could be synthesized using the isomerization of the double bond in Scabrolide B. This will be synthesized from the oxidation and simultaneous elimination of an alkene. The alkene will be introduced using Alkene Metathesis to construct the six-membered ring, and the dyeing required for this reaction could be generated using a Sigmatropic Rearrangement, which would also form one of the key carbon-carbon bonds linking the two halves of the molecule. This reaction requires a highly ordered precursor, and the authors could use an allylic sulfide for this. To produce this sulfide, they would use the halogenation and sulfidation of an allylic alcohol, and then couple it with the other precursor fragment. So let's start with the synthesis of fragment 1. The synthesis starts with R-carvone and the formation of a cyanohydrin at the ketone. TMS cyanide first reacts with the carbonyl and activates it, making it more electrophilic. The cyanide then adds to the hard electrophilic site to form the cyanohydrin instead of undergoing conjugate addition at the beta position. This nitrile was then reduced to an amine using lithal. This adds a hydride to the nitrile to first form an aluminium imine complex. Addition of another hydride forms the amido-aluminium complex, which is hydrolyzed upon workup to form the amine. This amino alcohol serves as a substrate for a Tiffeneau-Demjanov Rearrangement. Sodium nitrite is first reacted with acetic acid, which protonates it twice to form a hydroxonium that is eliminated as water. The resulting NO species then undergoes diazotization with the amine and is further protonated by acetic acid to generate the N2 group, which is expelled together with the migration of a carbon-carbon bond to complete the ring expansion and form the seven-membered ring, in addition to the oxidation of the hydroxyl group to a ketone. This reaction is driven forward by the loss of nitrogen gas, and overall, the product was synthesized in a 71% yield over 3 steps. The ketone formed by this reaction was then protected as an acetal using bis-TMS ethane and was taken forward without purification to an epoxidation reaction using MCPBA. This reaction, also known as the Prilazov reaction, involves the concerted addition of a peroxide to an alkene to form a bicyclic transition state where the forming epoxide is stabilized by the hydrogen bond between the terminal oxygen and the carboxyl oxygen. This produced the epoxide in a 77% yield over 2 steps. In the next step, the authors used this epoxide to install an allylic alcohol. Tetramethylpiperidine was first reacted with N-butylene, and then diethyl aluminium chloride was added to form the amido-aluminium salt. This was then reacted with the epoxide in order to form the allylic alcohol. The epoxide oxygen coordinates to the aluminium, and this directs the TMP to deprotonate the methyl group, promoting the elimination reaction to form the double bond. This double bond and the hydroxyl group are in the wrong place for the desired coupling, so the authors isomerized it by reacting it with mesyl chloride to mesylate the hydroxyl group. This was then reacted with aqueous sodium hydrogen carbonate. This promotes the elimination of the mesylate, forming the stabilized allyl cation, which was then attacked at the primary position by water to form the desired primary alcohol. Taking this forward, it was subject to chlorination with thionyl chloride. This acts as an electrophile and is attacked by the hydroxyl group, eliminating chloride. The chloride then acts as a nucleophile and attacks the activated oxygen, displacing it to form the primary chloride in its place. So let's move forward and look at the synthesis of fragment 2. This starts with the Alkene Metathesis of R-linalool using the Hyveda-Grubbs-2 catalyst. This catalyst first undergoes activation by reaction with the substrate. This is a formal 2+2 cycloaddition to form a 4-membered rutheniated ring. A cycloreversion then occurs and leaves a methylene group on the isopropoxystyrene ligand, which is eliminated, and forms a carbene with the substrate, which remains bonded to the catalyst. This then undergoes an intramolecular reaction to again form a 4-membered ring, which undergoes a reversion to complete the ring-closing metathesis and form the desired product. The catalyst is then eliminated, bearing the propylene carbene, and it goes on to react with another molecule of substrate, and the cycle continues. In the next step, the hydroxyl group was protected with TBS chloride, and then an allylic oxidation was performed using ruthenium trichloride and terbutyl hydrogen peroxide. This induces the abstraction of a hydrogen radical from the allylic position, forming an allyl radical. Further reaction with terbutyl hydrogen peroxide under ruthenium catalysis formed the carbon-bonded hydrogen peroxide, which is further oxidized to complete the formation of the enone. This was taken forward and used as a substrate for a Diels-Alder reaction. Aluminium trichloride was added, and this coordinates to the oxygen, making it more electrophilic and increases the reactivity of the enone. This was then reacted with butadiene, which reacts from the same phase of the molecule as the bulky TBS group. This contrasteric selectivity is unexpected, but has been reported before for similar systems. With the 6-membered ring now formed, the carbonyl was reduced using L-selectride. This adds a hydride to the less sterically hindered top phase of the molecule and formed the product in a 69% yield over 2 steps. The structure of this product was proven using X-ray crystallography, which confirmed the stereochemistry of the molecule. Taking this compound forward, it was then subject to ozonolysis. A 2+3 cycloaddition first occurs between ozone and the alkene. This forms a 5-membered ring, which then decomposes, breaking the carbon-carbon bond. This then recyclizes to form an ozonide. This ozonide then reacts with triphenylphosphine to form the desired dialdehyde. This dialdehyde is not isolated, and instead, the spontaneous addition of the hydroxyl group to the aldehyde occurs to form a cyclic hemiacetal. This was taken forward without purification and was oxidized with PCC. The hydroxyl group first attacks the chromium, and this eliminates chloride, which then comes back and acts as a base to deprotonate the carbon bonded to the oxygen. This eliminates the chromium species to form the desired carbon-oxygen double bond and complete the formation of the lactone. The remaining aldehyde was then reacted with sodium borohydride. This added a hydride to the carbonyl to reduce it to an alcohol with a 44% yield over the 3 steps. This alcohol formation was required for the next step, which was a Grieco elimination. Orthonitrophenylselenocyanate was first reacted with tributylphosphine, forming a phosphonium adduct upon the elimination of cyanide. This phosphonium species is then attacked by the hydroxyl group, which activates it as an electrophile, allowing it to be displaced by the selenide upon the elimination of triphenylphosphine oxide. The selenide is then oxidized using hydrogen peroxide. The resulting selene oxide then undergoes an E1 elimination similar to the Cope rearrangement to form a double bond and eliminate the selenol. This produced the product in a 44% yield, and the structure was confirmed using X-ray crystallography. This product was then reacted with lithium HMDS. This deprotonates the alpha position of the lactone, producing a nucleophile that was reacted with mesyl methyl sulfate to complete the synthesis of fragment 2 in a 95% yield as a single isomer. This stereoselectivity arises from the steric bulk of the molecule, as the electrophile must add to the convex side of the molecule, as the concave side is too hindered. With both fragments now complete, they could then be coupled together. Fragment 1 first underwent a Finkelstein reaction by refluxing an acetone with sodium iodide. This causes the iodide to displace the chloride, as sodium chloride is insoluble in acetone and precipitates out, which drives the reaction forward. This was then reacted with fragment 2 without further purification. Silver tetrafluoroborate was added as a halophilic promoter as silver binds strongly to halogens. This activates the iodide and makes it more electrophilic. The sulfide then attacked and displaced it in an SN2 fashion. This produced a cationic sulfonium product. The proton, bonded to the carbon bearing the sulfonium group, is very acidic as it is also alpha to an ester group and was deprotonated using potassium terbutoxide, forming a sulfonium ylide. This highly reactive species then underwent a sigmatropic rearrangement. The negative charge, resulting from the deprotonation, attacks the alkene, which then migrates, causing the elimination of the cationic sulfonium species. This was successful in forming the sterically hindered carbon-carbon bond, and the product was deprotected using TBAF, which allowed the different isomers to be isolated. Overall, this formed the SS isomer in a 31% yield, with a 33% yield of the RR isomer. The RR isomer was crystallized to confirm its stereochemistry, and this revealed an unusually long bond between the C12 and C13 carbons. This is due to the stereocongestion around this bond. Having served its purpose, the sulfur group was then removed from the molecule. This was done using tributyl tin hydride activated by AIBN to initiate the radical reaction. This radical first abstracts the sulfur, generating a carbon-centered radical which then reacts with another equivalent of tributyl tin hydride to form the carbon-hydrogen bond. This initially formed a mixture of isomers. However, they found that equilibrating it with DBU formed the desired isomer in a 79% yield. This product was then taken forward to a ring-closing metathesis reaction, using the same Hyveda Grubbs 2 catalyst that we saw earlier. This formed the central 6-membered ring in a 77% yield, and the ketone was then deprotected using MK10. This is an acidic mineral clay that has found many uses as a green catalyst. In the next step of the synthesis, they carried out another epoxidation reaction, this time using a vanadyl acetoacetonate complex. This reacts with terbutyl hydrogen peroxide, eliminating one of the ligands, and forming a vanadium-activated peroxide. Just as we saw in the other epoxidation reaction, this undergoes a concerted addition to deliver the oxygen to the double bond. This only occurred from one face of the molecule, as the complex is directed to the bottom face of the molecule by coordination to the hydroxyl group. This epoxide could then undergo a ring opening reaction. Reaction with triethylamine deprotonated the alpha proton to trigger an elimination reaction, forming the double bond and opening the epoxide ring to complete the formation of the allylic alcohol. This was then oxidized using IBX. This acts as an electrophile and is attacked by the hydroxyl group. The resulting intermediate undergoes an intramolecular deprotonation to form the carbonyl and eliminate the iodine species. This formed the product in an 82% yield. With this ketone installed, the final step to complete the synthesis of Scabrolide B was an isomerization, which was carried out using DBU. This is a non-nucleophilic base, which could deprotonate the position alpha to the lactone, and this forms a flat intermediate. Reprotonation of this position reinstalls the tetrahedral geometry. However, the favoured product has the lactone on the bottom face of the molecule, as this product has less ring strain. It was at this point of the synthesis that the researchers ran into a problem. Having synthesized both the proposed structure of Scabrolide B and its C12 epimer, they realized that the NMR data that they had generated did not match the data from the original discovery. This indicates that the original research group assigned the structure incorrectly, and the material that they had isolated does not in fact have the structure which they published. As the Forstner group had generated crystal structures for several intermediates and other related compounds, they could be sure that the stereochemistry of their product was correct. So more work will need to be carried out to figure out the true structure of Scabrolide B. Despite this setback, the researchers pressed on and completed the synthesis of Scabrolide A. A simple isomerization reaction using potassium carbonate was performed. This deprotonated the molecule, forming an enolate, which was then reprotonated at the alpha position. This formed the product in a 98% yield in just 3 hours, which indicates that Scabrolide A is much more stable than the proposed structure of Scabrolide B. This makes it unlikely that the proposed structure of Scabrolide B could be isolated as a stable material, though it does support the hypothesis that the proposed structure could be an intermediate in the natural biosynthesis of Scabrolide A. Well, that's everything for this week. If you enjoyed these videos, please like and subscribe. In the next video, we will look at irreversible inhibitors of botulinum neurotoxin A.